So I'm going to tell you a story about simulating physics. So this was an old story. This is a series of questions written down in the 80s by a very famous physicist asking about simulating nature, in particular simulating physics, using computers. The first one is, can you simulate classical physics with a classical computer? So a classical computer is what you use today. These are your laptops, your desktops, your supercomputers. The answer is yes, we can. Here's a great example of this. Does anybody know what this is? This is the active part. Sorry? Not quite the three-body problem. This is, well, sort of. It's a space telescope that we launched 2 Christmases ago. We know very well where it's going to be. We can simulate plasmas, which I have on the top. We can simulate fluid dynamics. These are all very hard problems computationally, but we can do it. We can put them on a computer. So that's a thing that's certainly doable. How about quantum physics? Can we simulate this on a classical computer? Well, so this is also an old story. One of the oldest interesting quantum effects that you can find is magnetism. This wasn't really understood until the middle of last century, so this is relatively new. A great example is magnetite. The Greeks knew about this, and it took us several thousand years before we figured out what's going on with it. And we figured it out through really sort of a very simple model of taking little spins, ups and downs, and putting them on a lattice and looking at their statistical properties. And using this, we can explain how you get from a magnet to a non-magnet as you heat it up, and these sort of very fundamental physics things. So suppose I want to put this on a computer, and I would like to model this whole thing, right? Well, I have one spin that has 2 options, another one that has 2 options, another one that has 2 options, and I have to list all of those. If I have 50 spins, this is how many things I have to keep track of. It grows really quickly. Exponential grows incredibly quickly. And that's 50 of them, right? That takes 18 petabytes of memory. And I really want a mole of atoms. I want 10 to the 23 of them. I don't want 50. It's not enough, right? So you can kind of do this, sort of, but a lot of people work on this. My group certainly works on this. I work with experimentalists. We try and simulate quantum systems. We do so by making use of supercomputers. These are 2 examples of ones that I've worked on that sit either at Oak Ridge in Tennessee or at NERSC in California. And we do all sorts of simulations, but eventually they run out of something. They run out of memory. They run out of computer time. They run out of graduate student time. We always run out of something. So the hope is that to say, well, I have 50 spins, I should just use 50 qubits, right? That's the idea, because that's what we're supposed to do. And this is what Hongchen was also talking about, right? Simulating nature, things you find in nature, things that Greg also mentioned. Okay, so, and this is what the area of research is, right? So can we simulate physics using a quantum computer? There's some really great examples of being able to do this that have come out in the past 5 or 10 years or so. Still very limited to sort of simple things that we could have done otherwise and sort of proof of principle demonstrations. This is an example from one of the early IBM papers where they studied hydrogen, lithium hydride, and beryllium hydride, which are very sort of simple chemical molecules, but really the achievement here is the fact that you got an answer at all. You were able to simulate this quantum molecule on a different quantum system, which is really impressive. And so this is what we do. We build a new software stack. Instead of a classical one, we build a quantum one, right? And all the things that you do as a physicist or as a chemist, you take in all your input and you go and you calculate things. But instead of doing this on a classical computer, you do it on a quantum one. Okay. So yes, we can do this. We have a lot of work to do before this becomes really a tool that everybody can use and a tool that the community typically relies on. I'm going to add one more question. Can I solve classical computing problems using a quantum computer? This is sort of new. And really, if you go look at any sort of, I don't know, consulting company or whatever that's going to find out what is quantum computing good for, this is what you're going to find. All these sorts of interesting applications that have nothing to do with natural sciences, which is fine, right? And so, where do you put radar towers or radio towers is one that was mentioned. Vehicle routing problems, all of these things have what I would call an unreasonably large solution space in that you simply cannot try all of them and check, right? That's what NP-hard means. Turns out you can map them onto the same problem. So this whole problem of having a simple magnet that we'd like to try and understand, you can use that same idea to try and to solve these types of problems that are of interest to people that are not natural scientists, but that are trying to solve everyday problems. So then having that, we can now make use of all of our fancy quantum algorithms that people are developing, that they're working on very hard. And it's gotten to the point where people are actually showing some results. So this is a result from Los Alamos National Lab from a few years ago, where a quantum computer in certain situations, and they kind of cheated a little bit. They picked a problem that nicely maps onto the quantum computer, right? But it came to a better solution faster than some of the other competing techniques, and these are the kind that you would find used in industry today for complicated optimization problems. What else do we have? Greg mentioned Shor's algorithm. We have very efficient algorithms for certain things that we need to do. Right, so Shor's algorithm in particular is a great example of this. We can use quantum algorithms for integer factorization, and these days we can use them for, and that as a building block is usable for a very wide variety of other computational tasks you might want to do. Okay, so can classical computing problems be solved by quantum computer? The jury's out, but we have some nice progress in this direction. And things I have on the right is, well, I figured I should show you some data that comes from a quantum computer. So this is actual data. Some of it's from 2019, some of it's from last year. It's a little noisy, and we work hard to try and figure out what can you best do with this and how can you still make use of it. And that's what we work on. Okay, thank you for your time.
No Paul Rudd, sigh. All right, if you have questions about what you've just seen, I have plenty of them. But once again, I am the host. You are the audience. Raise your hand. We will come out there and let you get those answers to your questions. We'll start right here. Then, Alicia, we can get the gentleman with the glasses. As I talk to the gentleman with the glasses.
Hi, I come from software background, and my question is, would the programming interface for quantum computers or quantum computing would be different, like traditional programming languages and stuff?
Yes, so the question was, are programming languages different? Completely. You wouldn't even recognize them. They are more like reading a music score, as you are trying to keep track of what the qubits are doing, and you're telling them, rotate this way, spin this way, interact with another one. And so it's much more like getting a bunch of, like trying to get resonance to happen out of a bunch of classical oscillators. So it looks very, very different.
All right, question from the back there.
Hello. Thank you so much for this very in-depth presentation. Excuse a question from a red wristband. Application-wise, I heard years ago the application of your technology, quantum computing, would very much disrupt the internet security space because every password would be able to crack. Could you speak about that a little bit?
Yes, I will warn you, I'm not an expert on encryption. The point is that the sort of standard encryption that we use relies on not being able to factor very large numbers into primes. If we were to get a quantum computer that is good enough, it could do exactly that. And that would break the encryption schemes that are based on that. Luckily for all of us, we have post-quantum encryption schemes that we can immediately implement, and so that it will not be an issue in that particular way. But it's going to be a little while before the hardware gets to be able to do that.
Don't panic. All right, question from the front here.
So I'll be honest, I've been kind of struggling to follow anything that's been happening in the last couple of talks.
That's okay.
But what I'm understanding is with each qubit is that, to kind of put it in traditional computing language, is that just sort of exponentially more parallel processing with each thing, or am I kind of missing fundamentally what it's doing?
No, you're sort of right. It doubles your memory for every qubit that you add, and also enables more. Yeah, your algorithms can run faster as well. So I think you're correct.
Better than I could have put it. All right, question over here.
Hey, if you had a idea or something and you realized it most likely could only be solved by quantum computing, what would you recommend to someone facing that idea? Would you say, throw yourself at quantum computing or try to redefine the problem?
I would first make sure that you are correct and that the problem is actually only solvable by quantum computers, because quantum computers are great, but classical computers are all absolutely amazing too, and we make new algorithms. And actually one of the really cool things is that people are taking quantum-inspired things and bringing them back to the classical world and improving our algorithms there. But after that, yeah, go and learn.
Thanks.
Yeah.
As Blue Oyster Cult said, don't fear the quantum. All right. We'll go over here. We've been over this side before. Oh, it's you again. Well, I should have stayed over there. Anyway, what's your question?
Another quick question. Did you hear anything about like solving the Shor algorithm? Like if there is any update on that, like using quantum computing to solve that, the factorization of large numbers?
Yeah, the largest number I remember, and probably my other panelists will know better, but the largest number that I know we factored is 15. It's not very large. Am I off base on that one? Yeah, that's about right. So the problem is our qubits and our gates are not very good yet. Shor's algorithm needs a lot of them, and so that makes it hard to apply to actual problems you care about. And so this is also why, like you see, Greg mentioned early advantage we might find in simulating nature or simulating other quantum things, precisely because these other things require a lot more resources and our hardware is not good enough yet.
All right, got a question right up front here.
Okay, why do quantum computers make so many errors? And are we paying enough attention to error detection and correction?
Oh man, we have armies of people working on error correction and detection. The short answer of why they make so many errors is because qubits like to interact with the environment. And when they do that, they lose some of their quantumness. We can quantify what that means, but right? So you now have a problem. You need to isolate them really well, but you would also like to be able to interact with them at the same time. And those are completely the opposite direction, right? And so you try and find a sweet spot between these sorts of places.
Sounds like my teenagers. I'd like to isolate them, but interact with them every once in a while.
He's not wrong.
God, I wish I was joking. Okay. Thank you, and I'm sorry for laughing at that. All right, sir, what's your question?
Hi, Lex. I'd like to try a different take. Let me ask you, Lex, 25 years in the future, put on your crystal ball. How do you see quantum computing making our lives better?
So I've learned not to make predictions. So the goal that, let me do the following. The goal that I want is that I want a quantum computer to be a working tool for the researcher in physics and chemistry, natural sciences, and maybe optimization. I have less insight into whether that's feasible or not. I don't think it will replace everything. I think it's going to be useful for certain problems. It's going to be amazing for others. It's going to not be. But it's going to be, because it's now a tool that people use regularly, there will be areas of science that we can answer that we couldn't previously. So this might be areas of catalysis. This might be areas of non-corrosive coatings for airplanes. They might be, there's a whole wide variety of sort of like very specific questions that we have in chemistry and physics that are, if we can answer these using quantum computers, that's what's going to impact your life.
All right, give it up one more time for Lex Kemper.